So first, let me give you a brief introduction of myself. So I'm Yuan from Alibaba Cloud, and I lead Flink storage team there. I'm also a member of Flink PMC and the committers, and my primary focus area is data management, fault-tolerance, and runtime execution. So today I will share some of the very exciting work we've accomplished in these areas. In particular, I want to introduce disaggregated state management target for Flink 2.0. And I believe this work is crucial to enable Flink's cloud-native future. So while this is not a Flink conference, so I will provide a quick overview for those unfamiliar with Flink. Flink is a leading streaming processing system for real-time data. It is widely adopted in industry used by many companies. It is one of the most active open source communities, and it was awarded in 2023 Sigmod Assistance Award. Now, Flink powers all the real-time computing business within the Alibaba group. So Flink has been around for about a decade and now used in a very wide range of applications, has various great features, support, and with rich upstream and downstream ecosystems. But stick to the root. If you ask me, what is the characteristics most importantly to Flink? I think it is three things. It's distributed, high performance, and stateful computation. Well, streaming processing, it has unbounded input, and it requires low latency and performs stateful computation. Like state here means the intermediate results of the processing up to a given point. So for stateful computation, these intermediate results are retrieved from the state store for each record. Hence, the state store access latency is crucial to the performance. State must be periodically snapshotted to ensure fault-tolerance. In a distributed environment, it is essential that these snapshots are consistent across all distributed tasks to maintain data integrity. By consistent, I mean for each task snapshot, it corresponds to the same input offset. On the right-hand side, you will see a simplified system architecture for Flink. State stores and operator processing are co-located using local disk to ensure extremely low latency of state access. The consistent checkpoint is performed by the checkpoint coordinator. The checkpoint coordinator periodically triggers snapshots of all the state stores. After checkpoint is triggered, each state store makes a local snapshot, and then the local snapshot is dumped to a durable storage after the checkpoint is triggered, like DFS. Upon a failure recovery, state should be reloaded, and those state stores are rebuilt. Well, this architecture works very well for a vast variety of workloads. The performance is good, and we also have made a lot of efforts to improve the checkpoint performance and to make the rescaling restore fast. Then what's the problem? Why we should talk about have this talk today? So to me, it is a bit old-fashioned and designed based on the hardware and network constraints about 10 years ago. The deployment mode and the business model have also changed. So overall, it's not a good fit for cloud native. So the biggest unfit is computation and the state store are tightly coupled, and they cannot scale up independently. Highly rely on local disk. Well, in early days, this probably not be a big problem because state size is relatively small, like hundreds of megabytes to gigabytes. So the tightly coupled issue won't be that much a problem, but people expect more as Flink grows more and more popular. So here is an interesting question that I pulled from the Slack channel of Apache Flink community. And this person is asking for whether Flink can support 10 or more joins and support infinite state. Well, the answer, of course, is no, because we know not any storage can support infinite data. But it's not uncommon for scenarios like logistics that requires hundreds of terabytes data for allowing tracking purposes. Because for logistics, it typically has to keep at least 2 weeks worth of data to keep in the state, and just in case, like if people want to return products, if we need to store more state data, we want to keep data in a cheaper way than coupled with the computation resources, and if we just have the state store coupled with the local disk. The second unfit is containerization. Containerization technology is commonly used today and a good fit for if we want to do the resource isolation. However, it also means resources pre-allocated for each container, hence best fit for stable and predictable resource consumption. But the current periodic checkpointing procedure is not a lightweight procedure, as all the state stores in all tasks create a snapshot, upload data, and perform compaction at about the same time the checkpoint is triggered. This can lead to a sudden burst of CPU network and the disk I/O of the entire cluster. So here it shows in the diagram that the spiky burst is actually caused by the periodic checkpointing. Like elasticity is another problem. Although we made a lot of great efforts, as I mentioned before, accelerating the restore and the rescaling procedure, but the state store relies on the local disk relies on the local disk and the local data to rebuild. It inevitably involving downloading the data locally first, and then it takes time for large state, of course. Well, luckily, the improvement of hardware and storage makes it possible to not rely on local disks. So we are very excited to introduce disaggregated state management in Apache Flink 2.0. The main change of the architecture is the shift from relying solely on local disk-based state stores to using a DFS as the primary storage. Now, DFS actually holds the active working state data and enable direct state access on DFS for operator processing. It brings us some significant benefits by making DFS as primary storage for state store. So state is no longer constrained by the local disk space allocated to the container. DFS data is directly accessible. This allows for instant rescale and recover, together with the feature like a hot update that we do not like cold start the containers. Since most of the state data has already resided on DFS when triggering a checkpoint, the amount of data flushed to DFS during checkpointing is significantly reduced as well, leading to a lightweight checkpoint procedure. So we do not see the burst of the resource usage as just we saw before in the diagram. It also, so this actually allows for the smooth CPU I/O network utilization. So what's more? So actually there are two more things I want to highlight here. The first is this aggregated state is a more flexible and extendable architecture that can potentially unlock more capabilities that we cannot achieve today, like state sharing and state querying. The other thing I want to highlight is the checkpoint procedure in Flink is to checkpoint state. That means the checkpoint mechanism intrinsically incorporates state, providing a built-in guarantee of exactly one semantics. So this is the characteristics other external storage systems do not have. Well, we have already talked about a lot of ideas. Now let's come to implementations. From this sketched architecture, it looks like a quite simple change, right? It's just shifting the state access from purely on local disk to DFS. Isn't that easy? It's no. The change brings a lot of challenges. So here lists some of the challenges when we are trying to shift the state store from the local disk to DFS. And these are the things that we have to solve before the disaggregated state management really work. The most critical one is actually the performance degradation. We know that disaggregation downgrades the performance, but for Flink, it is extremely bad. It is actually orders of magnitude worse than other systems. So async execution and async state access APIs are proposed to improve performance. Now, I will explain more why we have to do this way later. The second is we need a disaggregated state store to support writing to the remote DFS. So unfortunately, there isn't any usable open source version of this disaggregated store that we can use. So we decided to build our own one based on RocksDB, which is called ForceDB, ForceStream DB. We need to revise and improve checkpoint framework. We should make sure that the lightweight checkpointing is improved, and the restore procedure and the rescaling procedure, we can use the state data in the DFS directly to accelerate the restore and the rescaling as well. We need to cache and cache warm-up policy for cold start. We know that directly using the DFS does have the performance downgrading, and if we could use the local disk as a cache, why not, right? So this is to further boost performance. So since we've changed the execution model to an async way, then we have to provide async SQL operators. Because now all the DS operators and the SQL operators, they are all still written in a sync way. So correspondingly, the SQL plan and the fallback policy will also have to have a way to run together with the sync SQL operators, because we cannot have all the async operators just at once, right? And as I just said, the async data stream API should also be supported, and we have to provide possible ways for migrating the existing data stream jobs, and we should provide tooling for that as well. So as I said, among all of this, the async execution is the most critical and the complicated one, so I will spend the rest of the talk mostly focusing on this part, the async execution model. Async execution actually brought a lot of system complexities. Then the question is, do we have to do this? The answer is yes. We have a lot of discussion about this, and let me explain to you why we have to. So, like previously, as I mentioned, the disaggregation of the state store is expected to downgrade the performance a little bit. Like for example, for StarRocks, I think it's several times slower. But it is particularly slow and bad for Flink. The TPS dropped like 100 times when writing to DFS directly. So I think that's also probably one of the reasons along these years the remote state backend does not have any successful story. I never heard any successful story for that. So it's mostly due to Flink's synchronous execution model. So in the current synchronous execution model, input records are processed in a task thread, one by one, as illustrated in the picture. Yes. When the processing needs to access state, it's in the green color. The task thread is actually blocked, waiting there for the state access to return and then continue. On the left-hand side, I listed the access latency to various storage. You can see that the access latency to the remote object store, like OSS, is hundreds of times slower than the local disk. And that's actually why the reason you see the hundreds of times of the TPS drops. So the state I/O blocks the task thread 100 times longer in disaggregated mode. The task thread's CPU cycles are just wasted. And that's why you see the TPS jump. Well, then the natural idea is, OK, let's just make the state I/O access executed in a separate thread pool, making the task thread focus on the CPU thing, like the OP processing. That's a good idea, but it's not that simple because this causes new problems like ordering. Since state access executed in a separated pool, they can return out of order. Well, the out of order problem is probably the most challenging problem designing the async model in Flink. We have to make sure two things. The first thing is state accesses can be chained for the same input. Like shown in this slide, state 2 access is chained with the state 1 access. We need to make sure the chained state access order is kept. Or you have to access state 1 first and then state 2. The other way around it will generate wrong results. The second one is the order of records with the same keys should be preserved as well. An order of records with different keys, that does not matter that much because in a distributed environment, we do not have any guarantee for order between different keys. Well, in the current sync execution model, input records are processed according to the input order. Input record execution is wrapped in mails, like in a yellow square, and processed in task mailbox executor one by one. Then how we change it to async mode? Well, we do this way. We divide the execution for each record into 3 pieces. The OP process, which is depicted in pink, state access, which is depicted in green, and the callbacks of the state access. Notice that the callbacks may contain chain state access, as illustrated in the picture, right? This part. State 2 chained with state 1. So here is our extension for async execution model. In this extension, OP process and the callbacks of state accesses are executed in the task mailbox executor, like here. You see that? Yes. State access themselves are executed in a state executor in a separate threading pool, like here. After state access is finished, its callback is scheduled to execute into the task mailbox executor again, like here. Oops, sorry. So callbacks have higher priority to execute than input records to avoid too many unfinished inputs staying in the executor. So the middle async execution controller decides when and how to proceed with state access requests, this guy. Now let's take a closer look at the async execution controller. So why it needs to control when and how to proceed with the state request? Because it needs to preserve the execution order of the records with the same key. For records with the same keys, only one record is processed at a time. The following ones are buffered in the blocking buffer. For records with different keys, no execution order is guaranteed. For chained state access and callbacks, all the chain execution is finished before continue with the new records. Well, this actually introduced new challenges for checkpointing because when we trigger a checkpoint, all the input records before the checkpoint trigger must be completely processed before taking a state snapshot. In a synchronous mode, it's processed one record at a time, so that's quite easy. We only have one record on the fly each time. But in the async mode, many records are processed in different stages, and we have to drain the buffer before taking snapshot. Draining itself prolongs the checkpointing time, but let's be clear, it's prolonged the checkpointing snapshot time, not the uploading and the compaction time. So it has nothing to do with the lightweight checkpoint as I mentioned before. Even so, even like so, the prolonged time is within a controllable range because for inputs with high key collision rate, most state access is cached in memory, which should be fast. But for inputs with low key collision rate, the state access could be done with very high concurrency. That should not be too much worse than the current synchronous version. So in case if you really need a fast checkpoint, I just want to finish the checkpoint as soon as possible. So we do provide a way that you can snapshot buffer the state and their callbacks. We provide an interface that you can register your callbacks, and then when we restore those callbacks, you can execute the callbacks and perform the state access and re-execute the callbacks. So I talked a lot about details. I'm not sure whether you lost or not. And the asynchronous execution model involves a multitude intricate details, which I probably do not have time to cover them all here, and you probably not want to listen to much detail there as well. But I think that there one more thing worth to mention that I do want to mention is watermark. Watermark is used to measure the event time progress in stream processing. So the emit order of records matters for watermark. But since we do not promise orders between inputs with different keys, then they're out of order problem again here. So we solve this problem by segmenting inputs into watermark epochs. So input records are segmented into distinct epochs, guarded by the arrival of watermark. A watermark can only be emitted once all records within its corresponding epoch are fully processed and emitted. Watermarks themselves are guaranteed to emit in a monotonically increasing order. So in this way, we can guarantee the watermark itself is strictly kept ordered, and no record with timestamp smaller than the watermark is emitted after that watermark is emitted. Well, which is exactly the definition of watermark. There are some tricky things here about whether the order of the elements and the watermark is kept. But if you don't find the tricky things, I won't mention it. See whether people will ask me the question here later. Okay, we talked about a lot about the async execution and how we express it. So we provide a set of async state APIs. The state access results are encapsulated into a state future, which can be combined with state access callbacks. It's actually a very nice design, and I really like it. It's precise and simple. So here is an example that show how it works. We have this example. We first read the state, and then we update the states, and then we output the state value. So update and output are callbacks of state reads. Update and output are callbacks of state read, and the output is callback of state update. So this is chained callbacks of state update and of state read. See how fancy it is. Okay. So another thing that I want to mention is ForceDB. So we built our own disaggregated storage ForceDB to support writing to DFS. So ForceDB stands for full-stream DB. It is built based on the RocksDB 8.x version and integrated with the Flink file system interface. So it's by nature can support all file systems Flink support. So ForceDB can group and merge adjacent IO requests and fetch multiple keys within one batched IO to reduce the number of IOs and reduce the network round trip time. ForceDB supports a pluggable primary storage and cache, And ForceDB can share state and checkpoint files on DFS and enable lightweight checkpoint and faster restore and rescale. So the last part of this talk, I want to discuss a bit about the roadmap and the timelines of this whole thing. Disaggregated state management is targeted for Flink 2.0 release this December, hopefully. The goal is to the first version of the release, the goal is with 70% of the SQL async operator support with acceptable performance plus all the benefits we just described. And a preview version is planned to be published at the end of this September with SQL async join support plus acceptable performance and integrated with the SQL plan, like those integrated with the SQL sync operators, SQL plans, and all the fallback thing. The main goal for this preview version is to make sure this aggregated state management works end-to-end in an expected way. And we are under a tight deadline, actually. So here are a list of the flips that we are working on. So there are a lot of design details, and if you are interested in the technical details, you can take a look at those proposals. And those flip stands for the Flink improvement proposal. So there are a lot of work across the state team and also the SQL team and also the API team. So this is the current status of the project. The completed ones include like the ForceDB. So ForceDB now supports writing to DFS, and it has its repo management on the track with complete test and the release procedure set up, and it is fully integrated with Flink already. And also, we have built a unified async and sync state APIs, so ForceDB can work with both the sync API and the async API. So async execution, the most important and critical and difficult one, is also accomplished as well. Flink now supports both the async and the sync execution. Of course, we provide a way to bypass the async execution if it's not needed, and the async execution is still under experiment in experimental, like I noted that as experimental feature. So we also have a basic version of checkpointing and restore. So the ongoing work or the work left are async SQL operators. So we are actively writing those SQL operators. SQL plan and the fallback policy. We need to build a local disk cache. We need to ensure the promise of the lightweight checkpointing. Haven't done yet. And we also need to integrate with data stream APIs and also the things about the performance tuning. There are still a lot of mysteries that we do not understand right now in like the performance. Well, here are some very preliminary results. Let's be clear. This is a very preliminary. This is mostly to demonstrate the effect of the async execution model, because async execution model, in some way, it's make you to better utilize the IOs, but in the other hand, it's also has extra cost, to handle all those callback things and preserve key things. So in the simple read modify write word count scenarios, writing to HDFS directly, that's in the async mode. In the async mode can reach 40% TPS of the current sync execution on local disk. Remember what I just said, because in the very first version, previously we are almost seeing 100 times TPS drop. So now it's 40%. It's not that bad, right? So In this one, so if the async and the sync mode are running on the, both running on local disk, using nextmark Q20, that's the dual streaming join query. So nextmark is the standard streaming benchmark that we've developed and used to measure performances in a lot of cases for stream processing. So Q20 is IO heavy query. That's why we're using it as a target, the performance target. So the performance of async is 2x better than the sync. Again, this is, let me be clear, these results are very preliminary, and there are still some mysteries that we have to understand. And hopefully we can get thorough results after the preview version published, that's after the September. Okay. So these are the takeaways of my talk, and I've talked a lot of things, and I start very fast at the beginning, so it's probably ends a bit early. So first of all, Flink is a leading streaming processing system characterized by distributed high performance and stateful computation. So I think these three are the cornerstones of its design, which I even today, like Flink support so many different features, I don't think these cornerstones change that much. However, it's a little bit old-fashioned, not a fit for cloud-native era. So we introduced disaggregated state management using DFS as the primary storage. So to really make the disaggregated state management work, there are a lot of challenges, and among which I think the async execution is the key to make disaggregated state management succeed. So I spend most of the time of this talk to talk a lot of the details of why we need the async execution and how we solve the challenges of async execution. And we also implement our own version of ForceDB that can write to DFS directly. And yeah, hopefully we will have this aggregated state management in Flink 2.0, and it's targeted to release in this December. Thank you, guys. If you have any questions, I'm happy to take.